Hi, here are the notes for section 10.7, special segments in a circle. We've actually done some of this already. Uh, we talked about how a diameter can be a perpendicular bisector of a chord, or more importantly, if you have the perpendicular bisector of a chord, then you have the diameter. So we've already brought some of this stuff in, but now we're going to talk about other segments. What if two chords intersect that aren't diameters? What if a secant line and a tangent line intersect, and all that kind of stuff. So we're going to see a lot of stuff we've actually kind of messed with before, but in a little bit more complex manner. So first, you found the measures of diagonals that intersect in the interior of a polygon, parallelogram. Okay, now we're going to find measures of segments that intersect in the interior of a circle. And we're going to find measures of segments that intersect in the exterior of a circle. So, first thing we're going to do is we're going to go through a little quick proof, because here's the first theorem. And it basically says that if you have two chords in a circle that intersect, in this case intersecting point B, the part of one times the part of the two parts of one multiplied together is the same as the two parts of the other. So more importantly, to kind of see this, AB times BC equals EB times BD. So if you match the colors up, I got chord AC and I got chord DE. So AB times BC, so part times part, equals DB times EB, part times part. So let's take a look at the proof of this, because it's not really that hard of a proof. It just has been a while. So we have here, the same drawing. The first trick to this, and they've already done this for us, is that we have to draw in segment AE and segment DC. We actually have to create two similar triangles. And the reason is we're going to have to get two similar triangles to set up a proportion. Now, we already know we have one pair of congruent angles. We have a pair of vertical angles, angle ABE and angle DBC. Vertical angles, easy enough. So one, if I go through this, all this stuff here, given. Step 2, angle ABE is congruent to angle DBC. I'm running out of space. That's DBC. I know you can't tell, but it's DBC. That's vertical angles are congruent. Okay, now the next thing is we need one more pair of angles. Well, it might seem like this is going to be tough to find, but it really isn't, because we go back to a theorem we had a couple days ago. Angle E, or AED, and angle C, or angle DCB, are congruent. You might say to yourself, well, how do you know they're congruent? Well, look at them. They're inscribed angles. And what do both those inscribed angles have in common? They have the same common arc, AD. So, step 3, I'm just going to say angle E is congruent to angle C. There's nothing to confuse it with. And that's because the inscribed angles are congruent if they have same intercepted arc. Okay, so inscribed angles are congruent if they have the same intercepted arc. Step 4. Step 4 is, well, you're kind of done. Not as far as the proof is concerned, but proving the triangles are congruent. The tricky thing about step 4, though, is I got to make sure I'm right with the order. So angle B and B correspond, E and C correspond, making A and D correspond. So if I say triangle ABE is in triangle ABE, nah, not congruent. Similar. Ignore that. It's one problem with Sharpies is they don't erase. So ABE and DBC. And it was angles why they were similar. So once we have that, there are two more steps left. We really are almost done. I know you might not want to believe me, but we really are. Step 5, we have to start bringing in these segments of AB, BC, EB, BD. So I know AB and BD correspond to each other. So I can say AB over BD is going to be congruent to EB over BC. Okay, because part to part equals part to part. And that's just definition of similar triangles. Okay. If you're similar, you're your corresponding parts are proportional. And then for step 6, I'm going to cross multiply. AB times BC equals EB times BD. And our reason for that is cross multiplication. Sorry, running out of space again. And believe me, that says multiplication. So that's this theorem here. And the reason I bring it up is, again, we haven't seen a proof for a while, and this is a section that's kind of a good one to go back through. Okay, so there we are. Let's take a look at our first example then. So anyway, first theorem. So theorem 1015, segments of a chord theorem. If two chords intersect in a circle, then the products of the lengths of the chord segments are equal. So part times part equals part times part. That's the way I like to kind of describe it. And here's a simple example the book walks through, or not the book, the book's PowerPoint. So I'm trying to solve for x. So x times 8 equals 9 times 12. Excuse me. And then they just have x times 8 equals 9 times 12, 8x equals 108, x is 13.5. That's it. Nice and easy. Or they get a little more complicated as an example like this. So here's the more complicated example. So, yeah, basically, you'll have a question pop up to answer, and then, yeah, we'll go through it. All right, so here we go. Here's our problem. All right. So hopefully you answered that you would do x times x plus 10 equals x plus 4 times x plus 2. So that's what you should have said. Because that's what the theorem says. Part times part equals part times part if they intersect inside. Now the reason I kind of waited on this one is that it's really a pretty algebra heavy problem. So it's going to be x times x plus 10. And this is going to be x plus 4 times x plus 2. And we get to bring out our good old friend FOIL. Okay. On the left side, it's going to be a straight distribution. X times x is x squared. X times 10 is 10x. On the right side, x times x is x squared. X times 2 is 2x. 4 times x is 4x. I should probably be writing that out, shouldn't I? And then x times 2 is 2x and x. And then, yeah, 4 times 2 is 8. Okay. So x squared plus 10x equals x squared plus 6x plus 8. I don't care what side you decide to subtract an x squared from. It's going to cancel those guys off. So the algebra isn't going to be that bad to solve. It's just, it was to simplify it. And then we subtract 6x from both sides. 4x equals 8. Divide by 4. X is 2. All right. Next, whoops, example. Okay. Now the next couple of theorems aren't meant to be insane. The book has 2 theorems for this. You really could have 1. And the theorem is that you've got 2 segments that intersect outside the circle now. So in here, when it was inside, it was part times part equals part times part. Over here, they're both intersecting outside. Okay. And they both do the same thing. They really do. I'll probably flip back here in a second. But when you do this, you get the exterior segment of UY, or YU, times not the part, but the whole segment UX. So YU times XU, sorry, YU is way out here right now, but YU times XU equals the same thing as the other one doing the same thing. YW, or sorry, VW, gosh, I can't read my own letters. VW times UW. So exterior times whole equals exterior times whole. And you can see the products are the same down here. So the book has 2 of them, and again, I've just condensed it down to 1 just because I think it's so much easier that way. But theorems 1016 and 1017. If 2 secants or chords in a secant, okay, intersect outside of a circle, then the products of the exterior and the whole segments are equal. So AB times AC, right here, equals AD times AE, down here. Okay. On this one here, what happens is you get JL times JM, so exterior part times the whole. But on this one, since it's just a segment, the exterior is the whole. So it's exterior times whole. So that's why I just have it as 1. The book has it as this squared, but it's going to be JK times JK, which is the same thing. Okay. So let's look at an example then. All right. So again, the question will be, what would the setup be for this? And then I'll solve it on the next slide. All right, so let's take a look at this. So the first thing I'd say to myself is, oh, well, this is intersecting outside. Outside intersection, okay, that means I'm going to have exterior times whole equals exterior times whole. That's just the first thing I say to myself mentally. Okay, so let's see on this segment here. Well, what's the outside length? Well, the outside length is 10. So, okay, 10. And then what's the whole length? Well, the whole length is 10 plus 24, so 34. Okay, great. Now over here on this part, the exterior is 8. Okay, so 8. And then the whole length is 8 plus x, because I have to add them together to get the full length. So there we go. That's all our setup is. 10 times 34 equals 8 times 8 plus x. Now to solve this, it's just going to take, on the left-hand side, 10 times 34, which is 340. On the right-hand side, it's going to take a distribution, 8 times 8 and 8 times x. Subtract 64, 276 equals 8x. What's that going to be? I don't know, it's something and a half. It doesn't divide out evenly. So this is where we get out our calculators. Wrong button. 276 divided by 8. 34 and a half. There we go. 34.5. Okay. All right, another example then, after this one. Okay, the next example, really, even though it looks different, it's the same exact idea. It really is. So, again, the next thing will ask you what you're going to set up to do to solve this. Okay, so look at the problem again. Gosh, this barely fits. Let me just zoom out a little bit, I guess. Okay. So, there we go. That's the best I can get, I guess. I'm still looking, hey, this point intersects outside the circle. So that means I'm going to have exterior times whole equals exterior times whole. Okay. So look to myself, well, what's the exterior? It's 20. What's the whole length? 20 plus 25? 45. Okay. Now I look over here. What's the outside? Well, it's x. But what's the whole length? X again. Okay. So 20 times 45 is 900. 900 equals x squared. Take the square root of both sides. We end up getting 30 equals x. So we'll look at some more complicated algebra ones when we get into class tomorrow. Excuse me. But the same thing works for all the problems basically. Okay, great. Thanks.